Okay, so we have here today Mohammed Ali Rajabpour. Mohammed is a professor at Universidade Federal Fluminense, and he made his PhD in Sharif University of Technology in 2007, and he went through a couple of postdoc positions, the first one in the University of Turin in Italy in 2010, then at the International School of Advanced Studies in Italy in 2012, and at USP in 2014. I forgot to take note, when did you get the position at Federal Fluminense?
2014.
In 2014. So he's a professor there since 2014, and he works with physics related to statistical mechanics, field theory, and quantum information. And today he has a very interesting title for his talk, but from the abstract, what I got is that he's going to talk about Shannon entropy, phase transitions, and universality classes. So welcome, Mohammed, and the mic is yours now.
Yeah, thank you very much, Jason, and for the invitation to give this talk. Well, this is a talk that I've been giving since some months ago. The most recent one was in January, when it was the 70th birthday of Chico Alcaraz. It's something that we kind of almost finished it. So we have some we have a draft of the work, but it needs a lot of polishing. But it's kind of, we are almost at the end of the story. The reason that I picked to talk about this is that, you know, I've been busy working on this is kind of stuff for the last 10 years, starting with Chico Alcaraz in end of 2012, 2013. So it's almost 10 years ago. And after that, for a while, I did some mostly numerical works with some other colleagues of mine, Sona Najafi, who is now in IBM Watson Center, and then also another Najafi who's not related to the first Najafi, who is now in Akron, but is mostly who is based in Erbil University, and also another colleague of mine, Abul Fazl Rajabpour, who is in Shiraz University in Iran, and Rehane Khase, who is in Augsburg University. She's a postdoc, and Babak Tariqi, who is a student of mine. Well, I worked on this project with all of these people, but this work that I'm going to present today is based on the work that we have been doing with Natak Najafi Rajabpour in the last 4 years. So, well, as I said, the main reason that I'm picking to talk about this is just, you know, it has a long story, and one of the things that I've been so excited to work on for almost a decade. Okay, so the problem that I'm going to present here is actually, I can even present it to the high school. So what is it? Consider a matrix A, n by n. It can be any matrix. We can define the matrix, a submatrix of A, like Aij, with I and J going to be a set of the rows and columns of the matrix A. And then, so this Aij, whenever you see, is like, you know, you keep the rows in this of the set I and the columns from the set J. Now, if I and J are the same, we can use the notation AI. So this is like principal sub-matrices of the matrix A. Then if you calculate the determinant of this guy, these are things that we call them minors, principal minors. So you may remember these things from your high school. Now, the problem that I'm interested is that how can I calculate the sum of determinant of all of these principal minors power some alpha? Well, as simple as it looks like, you can just figure out that the number of principal minors are actually exponential with respect to the size of the matrix. It grows like 2 power n. So this sum is actually 2 power n. It has 2 power n terms. And well, in this talk, I will mostly concentrate on alpha, but this is a well-defined things for any alpha. Okay, so I'm interested to study this problem, and the first half of the talk will be about why we should care about it. So for alpha bigger than 1, an integer, it's proven that the problem is actually NP hard. So most probably there is no polynomial type algorithm to calculate it. So there is a proof that this problem for alpha bigger than 1 is a difficult problem, which makes it interesting also from the perspective of the complexity theory. Well, the first time that I was giving this talk, you know, I was watching this classic movie, and I kind of found it very timely with all these situations that are going on all around the world. So this is a famous dark comedy, and this slide is supposed to be some sort of a dark joke. Anyway, so let's go on and say that why I'm interested on this problem. So, well, first, this is the overview of what I'm going to tell you. First, you know, the first half of the talk is motivations, and then I will show you that sum of the principal minus power alpha can be written as a Grassmann integral representation, and then one can calculate that quantity using some sort of a mean field kind of solutions, and then I will apply it and show you an example how this can be applied to a transfer field Ising chain, and then conclusions. Okay, so what are the motivations? So let me start with the Renyi entropy of a quantum many-body system. So this is a very simple quantity to define. So you take a ground state of a quantum chain, let's say, which is written in a particular local basis. So I is supposed to be like, let's say if you have a spin chain with the spins 1/2, then you will have, for example, you can write the ground state in the basis of sigma x or sigma y, and then you will have a bunch of spins up. You know, these i's are going to be a bunch of spins up, or some of them up, some of them down, with different coefficients, right, amplitudes. Of course, you can do this in different bases. So depending on what basis you are choosing, the ai's are going to be different. And then the Renyi and Shannon entropy that you can find is going to be different. You know, these are the definitions that we have for the Renyi entropy and Shannon entropy. I guess these are simple stuff that everybody knows. And these PIs are the probability. So these PIs are probability of finding the system in particular configurations depending on that basis that you're choosing. Now, well, if you do something like this, you know, and minimize it over all the possible bases, you actually end up to the von Neumann entropy and quantum Renyi entropy. So what I have here is a well-defined thing. Sometimes people, they like to call it like a classical Renyi or classical thing, but actually I actually don't like that things, you know, because even the quantum von Neumann entropy is nothing except the same quantities, but minimized over all the bases. So just consider it like this. So in another word, you can also think about these probabilities coming from the diagonal elements of the density matrix. And if you actually diagonalize the density matrix, you will have a bunch of eigenvalues. If you use those eigenvalues, which one calls it Schmidt decomposition, you know, then you will have a quantum von Neumann entropy here and quantum entanglement entropy here. Anyway, I guess that it's very simple things. You have the ground state, right in basis, you have some amplitudes, take these amplitudes, calculate the probabilities, put it in this equation. So in quantum spin chains and some other quantum higher dimensional systems, I think you can calculate this. For example, let's say in the Ising chain, and then see how this scales with the size of the system. Well, these people, they did this like almost 13 years ago, but they calculated numerically, and then they realized that for a lot of systems that they studied, these coefficients of A's are non-universal, but the B's are universal when you are at the critical point of the system. So this was an interesting observation, numerical observation. That was also one of the reasons that I started getting interested on this problem. Well, so that was for the full system. You can do something similar also for a subsystem. So it means that you take your I, right, the configuration, so you divide them to A and IA bar, like, you know, you have the full system, and then you take part of it, you call it A, and the configurations in that part of the A are the I's, IA, and the outside are going to be IA bar. Now, you can calculate the marginal probability for that subsystem A using I mean, you just need to sum over all the probabilities, you know, so that inside is IA and outside can be anything. So this, we call it a marginal probability. And if you calculate something like this, then you can also define the Renyi entropy for the subsystem and Shannon entropy for the subsystem. Well, you may say, what's the benefit of doing something like that? Well, the benefit is that for one-dimensional systems, you can calculate these things numerically and see that, again, you have something which is linearly dependent on the subsystem size with some A which is non-universal, but there is a logarithmic term which the coefficients is X alpha. This coefficient ends up to be universal again. And well, this is something that we always like. When there is a logarithm, the coefficient is normally universal, and we would like to understand what is it. So extensive numerical calculations in the last, let's say, 10 years, which started with the calculations, numerical calculations that we did with Chico Alcaraz exactly 10 years ago, reveals that that the X alpha is actually dependent on the central charge. So this makes it, you know, interesting. Central charge is a quantity that we have in 1 + 1 dimensional critical system. This pops out as a central elements in the conformal field theory. Okay, which actually determines partially the universality of the system. Okay, so this was an observation, numerical observation that was mostly for some models. It was actually a proof. We had a proof, but for a lot of systems it was a numerical observation. Okay, so what was good about this was that this just needed you to measure in the system. You know, you prepare your ground state of the system at the critical point, and then you start measuring at each point the directions of the spins, and then you just calculate the probabilities, put it in the definition of Renyi entropy and Shannon entropy, and then you just get the X alpha. So I've been advertising this for almost 10 years to use it to calculate the central charge for the first time. And I was lucky that my colleague and friend Khadija Najafi got a job in IBM almost 3 years ago, and then she started implementing these things on the quantum processor of IBM, and now finally we have some results regarding the central charge of the Ising and X exchange in the yeah, the central charge of Ising chain and XX chain, we can now actually calculate it in this setup. And for that, you need a lot of special situations. It's a pretty hard work, but this is not something that I would like to talk much today about it. Well, if you are interested, I think Sona is the person who should give a talk about this. But anyway, so okay, so let me now come back to the special example, which is the transfield field Ising chain, because then I want to mostly talk about well, as an example, I'm going to try to calculate the Shannon entropy for this model. Okay, so it's better to fix some of the notations and stuff. So this is the most famous probably transfield field Ising chain, which is also realized in many different ways and experimentally. And this system has a paramagnetic and ferromagnetic phases, and there is a critical point. If H is equal to 1, then the ground state shows some critical behavior. Okay, so if you write the ground state in the sigma z basis and calculate the Rényi entropy for the full system, you can see that you will get something like this. This is the Rényi entropy with respect to H in the sigma z basis. And you can see that if you do the derivative of these guys, it actually blow up here and shows that there is a singular behavior at H equal 1, which is the phase transition point. And also you can see that the Rényi entropy is dependent on n, like this, with some coefficients. Well, of course, as I told you, this coefficient is more interesting for us because at critical point, it shows some universal behavior. So in this case, I'm saying that let's fix an alpha and then change the H. But another thing we can do is fix the H at, for example, yes, sorry. Now this is what this is later. So you can do the same thing also in the sigma x basis to just give you a simple idea. And using some Kramers-Vanier duality, the Rényi entropy in the x basis actually end up to be related to the Rényi entropy in the z basis, but with 1 over h magnetic field. And here, in this case, the B1x in the h bigger than 1 is 0. At h smaller than 1 is log of 2, and at h equal 1 is 0.2544. Nobody knows what is this number. It's a challenge to calculate this because we think that this is a universal quantity. Anyway, okay, so now imagine that we sit at the critical point, we fix the h, and then we change the alpha. If we do something like this, we get this kind of behavior. So now we are really at h equal 1, it's at critical point, and then the alpha changes. So up to alpha equal 1, we get something numerical. This is a numerical calculation, which is done, again, almost 13 years ago by this group of people in Saclay in France. So at h equal bigger than 1, we get log of 2, and smaller 1 is 0, and this is a coefficient which is universal, okay? And in the last 13, 14 years, well, as far as I know, some people really try to calculate this analytically, but they fail, and we finally have a way to actually calculate this quantity. Okay, but you may say, how is this related to the original problem of the principal minus power alpha? So this connection was made in 2016. We showed that the calculation of Rényi entropy is actually a SPPM problem. So I won't show you how this is done. It's a technical things, but well, but please accept that this problem of the Rényi entropy of the quantum Ising chain can be mapped to the SPPM problem. And with SPPM, I mean sum of powers of principal minors. Well, okay, so my motivation was to calculate this quantity in quantum systems, and that was the main reason. But then we also realized that, you know, and meanwhile, we also realized that you can write the Hubbard model partition function also as a SPPM problem, and we also realized that there are a lot of applications of this this SPPM also in machine learning. Okay, but the original motivation of today's talk is mostly calculating the Rényi entropy of the ground state. Okay, so how do we do this? So everything boils down to writing that quantity that I mentioned. So now I change alpha to n because now I'm just talking about the integer alphas, and now I have the n. So this n can be 1, 2, 3, and whatever, 4, 5. So so this is the main result. The main result is that you can write this quantity as a Grassmann integral representation. Well, it's a Grassmann integral representation is Bayesian Grassmann integration is a wonderful technique that I think it's very, very useful in many branches of physics. Well, so this is how it's done. You know, we have a bunch of Grassmann variables here. We do the integration over these guys. And there is a weight here, and this weight is basically this guy. So what is this guy? This AN is a block diagonal matrix. So these are the A's that we have, the matrices that we want to calculate the principal minus power n. We just put them, n of them. So we make n copies of the chi bar chi, the Grassmann variables, and then we couple them with this interactions, let's say. Well, the interesting thing is that this representation now is working for any matrix A. So any matrix A you can have, then the MNA can be written as this kind of Grassmann integral. Okay, so now that we have this kind of representation, we can play a lot of things here. So the first thing is that let's check how these things works. Well, for n equal 1, you can see that, you know, you can just put the n equal 1 in that equation. You have just one copy of chi bar chi, and then you will see that the MNA n equal 1a is nothing except the determinant of I plus a. Well, the determinant is polynomial. The complexity of calculating determinant is polynomial. So this is an easy problem. And well, I didn't claim that n equal 1 is complicated. I said that n equal 2 and other n's are more complicated, actually. So this is the complexity is the determinant, so it's more or less n power 3. But for n equal 2, we have this kind of integration. Here we have one copy, chi 1, and another copy, and then we couple them like this. Well, this may just remind you a bit the Hubbard kind of interaction, but I'm not going to enter to this story. But this kind of representations are also useful to go to and do bosonization using the Hubbard-Stratonovich and do all the calculations that I'm going to present today also in the bosonic form. But today I will just show you the fermionic version of these calculations. Okay, so that representation that I wrote for you has remarkable symmetries. By the way, I don't know that how do you, I mean, if somebody has a question, you can just stop me and ask now, or I don't know, or accumulate the questions for the end of the talk. I don't know how it works here, but anyway, I'm happy to stop if you have questions. Sorry. Okay, so this Bayesian Grassmann representation has some really remarkable symmetries, like UN symmetry, which mixes different species, and all of the subgroups of the UN symmetry, like UN1 and also U1, axial U1, the parity and sectorial parity symmetries. These are for generic matrices, and if also for we have the symmetric group symmetry, which is that you permuting all the copies, right? Also, we have the special symmetries if we have anti-symmetric or symmetric matrices. Like we have a particle hole symmetry if we have anti-symmetric matrix, and we have chiral particle hole symmetry if we have symmetric matrices. Well, the case that I'm going to present mostly today is about a matrix which is actually anti-symmetric. We have a couple of other symmetries too, like, you know, if you multiply A with some diagonal matrix D from left and right, this AD that you produce also have the same MNAD, which is what I call a diagonally equivalent symmetry. Well, all of these symmetries, they force some sort of particular forms on correlation functions, and some of them are actually broken in mean field description. So let me show you some of this story. For example, this is for general matrices. You know, what you can learn from this is that these are general matrices. This one is symmetric matrices, and this is anti-symmetric matrices. So depending on the general matrices or others, you can have different relations between the correlation functions. So we kind of classified all of the possibilities here. So for example, UN, we have already for the general ones, it forces us the equation 1 here, which we have here. Okay, so this is some sort of like a periodic table of the symmetries that we have. Okay, so now let's do the mean field theory of this this field theory kind of system that we have. And for that, we start by defining delta. Well, here I'm going to concentrate on n equal to 2. But one can do this the same kind of things for any generic n's too. So I'm going to define these deltas as this kind of correlation functions, and then I just write this 4-point couplings between the chi's as 2-point kind of couplings here. So this is the essence of the mean field theory, and the approximation is more or less equivalent to ignoring the fluctuations like this. Okay, so to further simplify the mean field equations, so I will put these two guys equal to delta 1, and these two guys delta 2, and this is delta 3. So now if you put these equations inside that integral representation, then you can do the integral, and that integral is the determinant of this guy, this matrix. Now, what are the consistency equations? The consistency equations here are these equations. So these are the consistency equations with the x is being this. Well, of course, you know, it's not important to follow all the details here. I'm just trying to give you the essence of how the things works. So, so I can write these consistency equations, and the nice thing is that depending on which of these deltas are non-zero, then I'm actually breaking different symmetries that I introduced before. So this is the symmetric group symmetry U2, U21, U1, SP, axial U1, and particle hole symmetry. Well, the interesting thing is that, so this is for the anti-symmetric matrix. So this is another periodic table, but I'm just showing you the anti-symmetric matrices. We have similar tables for generic matrices and also symmetric matrices. But why I'm just showing the antisymmetric matrix, because in the example of the transfer field Ising chain that I'm going to talk, there my matrix is actually antisymmetric. And remarkably, you will see that the case that is relevant for that example is this A7, which in that all the symmetries are broken except the axial U1 symmetry. Okay, so now you apply these things to the transfer field Ising chain, and well, it has some matrix pops out after doing some bunch of mappings, you know, and then now we have the matrix. Now we want to calculate the sum of principal minus power 2, which is related to the Renyi entropy with indices 2, right? So that's the whole point. Now, the consistency equations, they show interesting behavior. First of all, they came out, they are complex. So they have the real part and they have the imaginary part. Delta 1 is, and delta 3 can be non-zero for h smaller than 1, which is the ferromagnetic part, and they are 0 in the paramagnetic part. So exactly at the critical point, well, when I say exactly, I mean, there is a finite size effect, of course, you know, these are for finite sizes, but you can do this when the size increases, you can see that this breaking point, it starts to get closer and closer to 1. But delta 2 is 0. So as I was telling you, so the case that we have is this one. So delta 2 is 0, delta 1 is non-zero, delta 3 is non-zero. Okay, so and we can see that the delta in this region is small, the fluctuations, so we expect that our mean field works here better, actually. So here the results for mean field. So this is the R2 that we have, and then these are the exact numerical calculations, 16, 20, 30, and these are the numerical, the mean field results. So, well, of course, up to more or less 40 it's nothing special, because one can really do this numerically by spending 2 months on a cluster. You can actually calculate up to even 40 sites, but you need a good cluster and a month of running. But you know, so something like L equals 70 is out of reach for any possible computer or supercomputer or whatever. Anyway, so you can see here that there is a very remarkable agreement here around smaller than 1 in this particular case. And again, also here we show the derivative of this guy, and you can see that the mean field results start showing some singularity by increasing the L. So here we went to up to 100. You can go even further, but this was mostly just a proof of principle. And also, it's possible to calculate those coefficients that I told you that they are universal. So if you sit at the critical, if you want to calculate the alpha 2 and beta 2 with respect to the edge, you can also calculate it. And here, this exact numeric means that it's a numerical calculation, and this mean field is this guy. Well, there is a bit of discrepancy here, but these discrepancies can be resolved with some other techniques by going to by doing some sort of a duality and kind of things that I'm not going to talk about it. So we already figured out how to resolve the problem of discrepancy for very small h's. Now, even for h equals 0, we almost have a perfect result. Yeah. So this is working. So I can give you a few more comments before closing the talk. So interestingly, in the ferromagnetic regime, all the symmetries except the axial U1 symmetry is broken in this model. I just mentioned it. in the negative transverse magnetic field regime, the fluctuations are big, and the mean field should be applied after proper duality transfer. This is also under control. So even if you go not h equals 0, which looks like an extreme point, if you go further, you need to do some massage. So the 2-point functions show interesting scaling behaviors around the critical point that I didn't talk about it there. You can write some hyperscaling relations for the 2-point correlation functions. And of course, it's funny that the mean field theory works for the 1D Ising chain. Normally, we say that the mean field doesn't work. Well, of course, it depends on what quantity you are interested in. For the calculations of Shannon, for the calculation of Rényi entropy, here we have a very good mean field theory, which is appropriate. So the general comments that I can give you are the things that we have done, but I didn't talk about them here. So we also did calculate the SPPM problem for the discrete Laplacian matrix in 1D for some other reasons. So this was actually an exact calculation. It's a kind of, things that in the beginning it looks simple, but then when you start it, it's just pretty non-trivial calculation. And then when we checked it with the mean field results, it was very good results. So this discrete 1D discrete Laplacian is actually symmetric, and there also one can look what happens to the symmetries and interesting stuff. So hyperscaling relations around the phase transition point can be derived for this new field theory. This one I just told you, but I didn't show how this is done, but it's doable. Then the Berzin-Grassmann representation can be used to find also alternative formulas useful for the numerical calculations and also analytical calculations. As I told you at some point, for n equal to 2, you can write you can use the Hubbard-Stratonovich kind of transformations and change and bosonize those integrals that I told you. And when after bosonization of those systems, you can start trying to calculate if you do the discrete, if you use the discrete Hubbard-Stratonovich transform, then you can do the Monte Carlo. But if you do the continuous one, then you can use some techniques of calculating integrals, approximate ways of calculating the normal integrals. And then we did these things, and we got this similar kind of mean field equations as the ones that I presented to you. But there we can also check that our results are actually stable. So we can also check in that method the stability of the mean field solutions, because of course we don't expect that it should work for any matrix, but we have a criteria which says that the mean field solution is how much it's stable and reliable. Yes, so we have also developed other methods that are useful for specific matrices. So if the matrices have some specific properties, you can also develop some other kind of methods. But these are not things that I'm going to enter in this talk. So to summarize, the SPPM is useful in the calculation of the Rényi entropy and in machine learning and many other places, well, I've seen. Then we found a new Berzin-Grassmann integral representation for the SPPM problem. The new field theory-like representation has some remarkable symmetries. Application of the mean field on the new representations gives good estimations for the Rényi entropy of the ground state of the transferred field Ising chain. It detects the phase transition and provides nice hyperscaling relations and good estimate for the universal quantity. So the physical example that I showed you was the transverse field Ising chain, the ground state, and the Rényi entropy of that. As far as I know, this is the first analytical calculation of this quantity, which has been resisting the analytical calculation for the last more than a decade. Okay, thanks for your attention. I'm here if you have questions.
Okay, thank you, Mohammed. Sorry, it took me a while to turn on the mic here. Thanks for the very nice talk. Now I'm going to open for the audience and for the online participants here. If you have questions, please open your mic or write something.
Hi, Mohammed. Javier.
Hello. Oi, José.
Can you show your slide 27, I guess? Can you hear me?
Yes, but it's a very, the voice is not clear.
I told you to check slide 37, if I heard
27.
27. Xavier, if the audio is not good, maybe you can write down the question.
Yes, maybe you can write it down if it's not working.
Can you show the slide 27?
Xavier is writing.
Okay, so where should I see this?
There's a public chat.
Okay. I need to go to slide 27. Okay. So 27 is here. Yes.
Yes, that one.
Should I make it? If I make it big, then I won't be able to see the message.
Can you hear me, Gerson? Yes, the problem is if.
So it's really a bit noisy, but I can hear you.
So it's appears from here that you can use your method to detect critical points, right?
Yes.
So is there any advantage to use your methods from the others? One, like the crossing the gaps or use the entropy?
So the reason that in the beginning I was advertising about the central charge, for example, was that this is a quantity you really can go to the experiment. This is the simplest things that they can measure, right? So you ask them the experimental, you prepare your ground state for any edge, and then just measure the sigma z, sigma x, right? And then you get the quantity. Well, theoretically, of course, you can do many things. You can say that I have the excited states, the gap, all these things. But those things are just good for theoretical investigation, right? Experimentally, they are not doable. Well, at least not easily doable, I guess. It's much easier to just have the ground state and then just measure the spins.
Okay, thank you.
Nothing.
Okay, any other questions? The audience, or questions? Okay, I have kind of a question. You were showing results mostly for the Ising case, and as you said, in the end, it's pretty much the first calculation for this kind of results. So what about in the abstract? You mentioned other systems like Hubbard and so on. Do you have results for other Hamiltonians already, or? Well,
yeah, we can do similar calculations for all the spin chains that can be mapped to free fermions, like the Ising one, like cluster models and stuff. These are the things that we can do. But if you ask, for example, XXZ, at this moment we don't know how to do that because it's not something we can map it to SPPM problem, how to map it, or we are not even sure that it is, but might be some perturbation over SPPM but this is something that, you know, needs a thorough investigation. So let's say that we know that all these things are going to work for all the cluster spin chains and all the free fermions in any dimension. But for those that interacting kind of so-called interacting kind of spin chains like XXZ, we don't know yet how to use this technique.
I see. Okay. Okay. Thank you, Mohammed. I guess there is no other questions, right? Okay. So I'm going to stop it here and thank Mohammed again. Cannot hear, but we are clapping.
Yeah. Thanks for the invitation.
Thanks very much. And just remind you, we're going to put this talk on YouTube later. Okay.
Okay. Okay. Thanks.
Thanks, everybody.
Have a good evening.